Hey everybody, what's good? What's going on? JB here, back with another CyberInsight live stream. Today we're going to be circling back to some sweet Cisco BGP lab action. So it's been a minute since we've done any of that. Started off, I think, what was it? Maybe a few months ago, we were doing some OSPF labs, and then we started and did a first BGP lab. We were kind of looking at a single AS BGP environment, dealing with the route reflectors and stuff like that. Well, in today's lab, we're going to hop in and take that a little step further, start to deal with BGP Confederations, which if you haven't heard of that before, then this is going to be pretty fun. So I'm going to hop over into my other browser and we can just jump right into this. As always, make sure you smash the like button, subscribe to the channel, all that other good stuff. And yeah, throw questions in the chat as we move through this. All right, so here is my GitHub page. If you remember from last time, this is where all the different labs are. I can kind of show you some of the different ones, the OSPF labs, BGP labs, all that good stuff. Have a link for this in the video description. So BGP Confederations and Path Control. So if you remember, I have both base configs that you can use to get your environment set up, and then final configs, which include all of the different configurations that will be including the different tasks and stuff like that that we cover. Also, if you're using Cisco CML, then there's a BGP lab .yaml file that you actually can use and load that into CML, and it will pre-populate everything for you. So pretty cool. Makes things a little bit easier spinning stuff up. So looking at what we're going to be covering in today's lab, we're going to be looking at as I mentioned, confederations. We're going to do a little bit of a dive into what confederations are and kind of the reason why we would want to use those. We're also going to be setting up OSPF as the underlying interior gateway protocol between all the different routers in this environment. We're going to be looking at doing some BGP network advertisements, and then we're also going to be looking at AS Path Filters, specifically using Regex to be able to help set some different filters as far as determining which routes we want to take in an environment. So if you haven't messed around with Regex before, and specifically AS Path Filters, then this should be helpful. It is a little confusing, but we're going to work our way through it, and I think you'll take something positive away from it. So let's see. Anything else I want to cover on this before we jump into it? Just high level, the tasks that we're going to do. Set up host names, interfaces, IPs. That's actually already done in my lab environment, so we don't need to do that. Task 2, we're going to configure loopback addresses on all of these different devices. I think we mentioned before, maybe in the BGP lab and the OSPF labs, the reason why we like to use loopback interfaces as what we use to source routing updates from. And that's primarily because we can have this loopback be up and it's not dependent on a particular interface being in a up state. So if you run into an issue where there's connectivity issues and maybe the interface that you were using to send out routing advertisements goes down, if you're actually using a loopback and you have multiple or redundant physical connections coming off of your devices that connect back into your network, then that just makes things a little bit more reliable. So we're going to do loopbacks. Then we're also going to enable OSPF between all 4 of these different devices. The only advertisements that we're going to be doing with OSPF is the /30 links between the devices and the loopbacks. So that's going to kind of get our connectivity between all these, and we're going to rely on our BGP configurations that we're going to be implementing to actually route the different LAN /24 subnets. The next step after that is going to be step 3, and that's where we're going to deal with BGP confederations. So we're going to be talking about confederations. Like I said, we'll do a little bit of a deep dive into that. Then we're going to be setting up BGP on each of these devices, setting up our neighbor addresses. the way that we're going to be doing this and the purpose that we're going to be doing this is we're going to have these different sub ASs that are going to be associated with certain devices. However, to the external world, and this is one of the benefits of confederations, everything that those sub ASs are a group of actually appear to external routers that would be connecting as a complete or whole AS. So in this case, we want it to appear to be AS 254. Fourth step is we're going to then take the /24 LAN subnets and advertise those via BGP. At that point, we'll make sure everything can connect to each other. And the last part, dealing with the different types of path control. We're going to be looking at kind of some potential future changes that we might do here. So we're going to plan for a future link between router 1 and router 3. However, what we want to do is we actually want to make sure that router 1 and router 3 actually will prefer networks or routes to each other's network through the AS 6502. So in essence, if this link were to be here and we were down in this AS 6503 and we're coming from LAN 3 and we wanted to get to LAN 1, we want to have it prefer for the traffic to go all the way back through 6502 over to 6501 versus taking this connection between 6503 and 6501. So there's some ways that we can do that. And in this one specifically, we aren't going to be using IP ACLs or prefix lists. So that's going to actually require us to do some stuff with Regex. So that will be kind of cool to play with that. So I think that is pretty much just a high level breakdown of what we're going to be covering. Got any questions? Throw those in the chat as we move through it. And I'm going to move over into the lab environment and we can start to get these configurations up on these different devices for the Loopbacks and OSPF. So let me make sure that you can see this. I'm going to pull this down a little bit. And that might have went down a little bit too much. We just want to make sure that we're looking good there. Okay, let's see. Perfect, that looks good. Okay, so we're going to get in here. I'm going to show you what we need to copy over here. So loopback 0, which if you remember on router 1 is 1.1.1.1.32. And then we're going to be doing just a very simple OSPF configuration. Now, in order for us to do what we want to do OSPF-wise, if you remember, we wanted to route the loopback and the /30. So we're going to advertise loopback, and then on this interface here, we're going to make sure that it's part of the same OSPF area. And then we're going to do the same thing on each of these other devices. So we're just going to scroll down here, interface loopback 0, 1.1.1.1, and it's going to be IP OSPF area 0. We actually can just do the OSPF portion first. So we're going to make sure that it's going to have a router ID of 1.1.1.1. And remember, this ID here doesn't matter so much. You can make it be whatever you want across the different devices, but we're just going to make it simple and go with 1. And then we're going to copy over the interface, loopback stuff. So the IP address, this is a /32, and then we're going to put it in area 0. And so everything that we're doing is just going to be in area 0, which is the backbone area of OSPF. And we'll just see how this looks. That looks good there. And that looks good there. All right, so we won't really be able to see anything with that until we get this next one up on router 2. But the configs for the rest of these is pretty much the same. I mean, the only difference here is the specific IP addresses that are corresponding to the loopbacks. So let's move this. We'll go into this guy. And conf t. Let's get that. That's kind of, that white space there is a little annoying, isn't it? Okay, that's a little bit better. And we'll copy that over. And then we'll do the interface loopback. And then after we do this, and we should actually be able to see that OSPF ends up coming up on this. So it should be able to do like a do show IP route OSPF. Let's see. Might take a second for that to come out. Oh, you know what? I mentioned it and forgot to do it. We actually have to make sure that we add the OSPF on the interfaces. So we either have to add it on the interfaces, the specific interfaces, or we have to add it on just a network statement in general. So like for the /30. But let's just do that here. So this is going to have to add it on GI00 and GI02 off of here. Do that. And then GI02. And then let's go back and do it on router 1. That's going to be on GI00 as well. GI00. Okay. Now if we go back, and run that same command, the do show IP route OSPF. Oh, that wasn't in config mode. Let's see, show IP route OSPF. Let's double check. So that is going to 00. Could check the neighbors. Okay, yep, so that's a full state, which is what we want to see. There we go. Okay, now we're seeing that there. Full state should be good on the other one. So let's just go down to router 3. Get that config on here as well. And again, we're going to add the loopback 0 and the OSPF commands. And we won't forget it on the interface this time. And then let's add the interface, loopback 0. And then we also have to add that IP OSPF 1 area 0 command to GI00. All right, and now the last one, and then we should have OSPF up and running, and we should be able to ping between the loopbacks and stuff like that. And then once we make sure that's good to go, then we're going to do our little dive into BGP confederations and why they're needed. All right, we're going to move over to router 4, grab the OSPF portion here. And then interface loopback 0, and then we're also going to need to add that same OSPF command on GI01 and 02. Let's go interface range GI01-2, just to make it quick. And there we go. So let's do show IP route. That might take. There we go. Now we're seeing all of these coming in, 1, 2, 3, and 4. 4 being the directly connected one. The rest of these coming in from OSPF. We can see that there. And then we can see these other ones coming in. So the only one that isn't directly connected would be the 10.0.0.0. We should be able to just ping some stuff at this point. Yep. And that pretty much should show that we're able to do what we need to do, but just for the sake of being thorough, we'll go ahead and hit everything. All right, so that should be good. Now, let's talk a little bit about BGP Confederation. Now, there's a few different web pages here that kind of have a breakdown of some different things. I've put these in the description of the video, so that should help you out if you want to do a little bit of a deeper dive with this, because I'm just going to kind of hit things from a high level. So before, in the previous BGP video that we did, if you remember, let's see, I'll pull it up. We don't need that to play, though. Let's not do that. Well, in the previous video that we did, it was a single AS environment with multiple routers, and we were dealing with the issue that in a iBGP environment, all of the different devices have to be fully meshed in order for them to talk. And so you see it was like 65,000. And the solution to get around this was to actually have route reflectors. So if everything was going to be fully meshed, then that would mean every single device would need to have a connection to everything else. And in something this small, yeah, that would work. But once things really start to scale, you really can't really do that. So route reflectors gave us the ability to identify certain devices that would be able to share routes with other internal BGP peers that aren't directly connected. And that's great, and that works, but there is another option that we have to get around this requirement for having fully meshed iBGP peering, and that is something called confederations. And so what Confederations allows us to do is, instead of having a fully meshed environment of one AS, we have like the high level primary AS, and this is what everything else that would be connecting to it outside of our environment would see. But then within that, we're able to create sub ASs. The sub ASs allows us to reduce the number of required iBGP peerings. So within the sub IS, or within the sub AS, everything needs to still be fully meshed. But the connections between sub ASs don't require everything to be fully meshed. So you're able to cut down on this quite a bit. So you kind of see some examples here. This blog post here, though, is actually excellent. So I did want to spend a few minutes just kind of hitting on some of the main points within this, because there's some unique features to this that even though we end up creating this confederation, it has the sub ASs within there, which in essence is running iBGP. It looks like it's doing eBGP, which is what you'd see between different asynchronous systems. However, it still has some unique characteristics as far as the types of data that it's exchanging back and forth that is very similar to iBGP. So we're just going to kind of read through this just a little bit. So why would we want to implement this? So we're talking about that an AS, or autonomous system, can be split into multiple more manageable sub ASs, each of which has its own AS number, and BGP Confederation allows us to apply a scalable approach when it comes to this type of deployment. Again, we're talking about trying to limit the need to have fully meshed connectivity between iBGP peers. The reason why we want to do that is because it will consume, if we do that and we really try to have, everything peered, it's going to really, or has the potential to crush CPU utilization and add a lot of unnecessary traffic and things like that, especially if you're doing it across something that's probably a little bit larger than what we're doing in this lab scenario. So when dealing with iBGP scalability, we have two different options, and that's what I mentioned. So we have the confederations or the route reflectors. So there's different reasons why you would want to choose one over the other. For route reflectors, we don't really have to deal with all of the additional configuration changes that come with identifying sub ASs. And depending upon how your environment's already set up, you might need to do a little bit of re-architecting and topology configurations to kind of get everything working. That's great. BGP route reflectors work. It's pretty simple. I've used those before in environments. So that's pretty cool. And especially works well if you're just using a single internal gateway protocol between all of those. In instances where you aren't doing that, though, you might want to end up looking at using BGP confederations. So there is a little bit more of a configuration architecture, I don't want to say challenge, but a little bit more work and thinking that ends up going into it. But the cool thing is with the confederations, you can have different IGPs within the different sub ASs. So if you have an environment that has different types of devices that are able to support different types of IGPs, or you have a very, very large enterprise, maybe it's a global, and there's certain types of IGPs that are using different places for whatever reason, then confederations might be the way that you want to go with that. So kind of mentioned how it works as far as splitting one AS into several sub ASs. All of the BGP speakers within sub AS need to be fully meshed. So you can kind of see that here. You can use private numbering for the different ASs. The connection between them is always eBGP peering, but it's also referred to as intra-confederation eBGP. That's what we're talking about here. EGP routes that are exchanged between sub-ASs are known as confederation external routes. Does this really matter as far as what we're going to be doing in the lab? No, but if you are studying for the CCNP or CCIE, that might make sense to be able to know a little bit more about this. And again, please go back and actually do a deep dive on this blog. I think it's pretty good. The interesting thing with the way that the path is chosen here is eBGP routes that are exchanged between sub-ASs, as I mentioned, are known as Confederation external routes, which are preferred over iBGP routes when it comes to the best path selection. If BGP has to choose between two paths to the same destination, one path leading inside the sub-AS, so let's say here going down to here, and another going outside the sub-AS, so here going over here, it will choose the external path. So it's going to prefer to go this way towards a neighboring sub-AS. If it has to choose between a Confederation EGP route and an eBGP route that leads outside the Confederation, then it will choose the external one. So again, if we're talking about it has a route that's going to go this way, still within the Confederation, versus one going external to a whole nother AS, then it's going to prefer that one to go outbound. So there's some loop avoidance mechanisms, and that's primarily the AS path. And the AS path list that's exchanged between the eBGP peers within the Confederation, again, here to here. It's used to detect routing updates leaving one sub-AS, returns to the same sub-AS. If it sees its own sub-AS number in an AS path list, the sub-AS will not accept that routing update. So it goes a little bit into the AS path attribute. You can dig into that a little bit yourself. Trying to think anything else. It's kind of interesting. Oh, one more thing to keep in mind, eBGP peering within the Confederation. In the case of all sub-ASs run the same IGP, attributes such as next hop, med, and local preference do not change when routing updates is traversing the Confederation eBGP connection, as opposed to standard eBGP. So what does this mean? It means that sub-AS exchange routing information as if it actually was iBGP, meaning this back and forth here will exchange local pref and other things that you normally would see shared within iBGP, even though this is kind of a eBGP type of connection. Let's see, anything else in here? I don't think so. I think we can kind of hop over into the lab and actually start configuring this. The breakdown here, talking about how it helps with fully meshed iBGP environments. There is some challenges with migrating. Again, especially if you end up wanting to use different types of internal gateway protocols, then this would be the way you want to go. Something also kind of interesting, depending on how large your architecture is, you actually can use route reflectors within each of the sub-ASs. So even if it was kind of gigantic within that, and you didn't want to fully mesh within your sub-AS, you can use route reflectors within that. So pretty cool stuff. So let's get back over into the lab here, start up on router 1, and take a look at what we are trying to do. So we were going to do the BGP Confederations as we kind of had outlined in the other diagram. We'll just pull that up real quick for a refresher. So BGP Confederations, we're going to use Loopback 0 for peering for BGP. We want the external world to see everything as AS 254, even though these are the sub-ASs that we're going to be using. Anything else that I want to hit on that? I don't think so. I think that probably is pretty much what we need to do. So let's just kind of look at the different commands that we have that we're going to be using here. So from a BGP perspective, it's pretty straightforward. So we are going to create the AS 6501 on router 1. And then the BGP Confederation identifier. Remember, that was going to be 254. And then the peer that this is going to connect with, remember looking at the diagram, should be 65502. This is what this sub AS is peering with, the 65502. So it's BGP Confederation peers 65502. And then we're going to go neighbor 2.2.2.2, remote AS, that same one, the 65502. Now we want to be using the loopback 0 is what we're sourcing BGP from, so we're going to go neighbor, update source, it does help when I put the IP in there, update source, loopback 0, and then we need to do this because we're going not from like the interface that's directly connected over to that neighbor, but because we're going from loopback, we actually have to use the eBGP multihop command. So we're going to go neighbor 2.2.2, and it's eBGP multihop. Now, when we're configuring this on router 2, for instance, and we have that other connection down to router 4 that's within the same sub AS, since that's not eBGP, we actually don't need to use this command. So you'll notice that that'll be a difference when we do that. Okay, so that's all we needed to do on router 1. Now that I kind of showed you what these different commands are, for the rest of these, I'm just going to go back to GitHub and copy and paste in what we need to do. Let's get in here. All right, let's go take a look. So we're going to go router BGP 6502. And then we're going to do the Confederation identifier and the peer statement. Again, so this peer is going back to what's on router 1. Now, as far as neighbor statements, back to router 1. Remember, that's using that eBGP, so we got to go the multi-hop. And by me just entering that like that, I think it automatically puts to 255. So depending on how many hops you wanted to do, you can specify that if you want it to be less. But I think if you just leave it without putting anything there, then it puts in the max that it could be, which is 255. And then the update source. And we'll go and add that in. Now for the other connection, remember this one is actually going down to router 4. That's in the same sub AS. Then since it's in the same sub AS, there isn't necessarily going to be a different statement, obviously, for the peer, and there's no eBGP multi-hop needed there. So we can just copy these in. And I should, on this guy, do show IP BGP summary. Yep, so we can see that we already have a BGP connection to 1.1.1.1 and that's to AS 65501. So that's been up for 52 seconds. Obviously, the 4.4.4.4 isn't going to be showing anything yet because we actually haven't configured it yet. So let's get into that guy. If you have any questions at this point, please throw those in the chat. I will try to answer them the best I can. So this should all look very similar. So 65502, same sub AS as what was on router 2. And then same confederation identifier. Now this time, since this doesn't have a connection anywhere except back to router 2 and to router 3, going to router 3 is that connection to 65503. So we're going to take that. And then we're going to do the neighbor command going to 2.2.2.2. And the neighbor command going to 3.3.3.3, which again needs the eBGP-multihop command. Do show IP BGP sum. Let's see if this comes up. There we go. So now our internal connection back to router 2 looks good, and the last thing we got to do is go on router 3 and finish this off, and that will wrap up task 3. Let's see. Router BGP 65503. Go ahead and drop this in. Okay, and then BGP Confederation identifier. The peer connecting back to router 4. And then the neighbor statements. Okay. And that should be good there. To show IP BGP sum. And that is up. So that should be good on all of those. Let's see, do show IP route. And we shouldn't be seeing any specific routes being advertised yet because we haven't done that yet. And that should be good. So the next step that we have, remember, was to actually advertise the LAN subnets. So on router 1, advertise 192.168.1.0/24. Router 2 is .2, router 3.3, and router 4.4. Now this is very straightforward. All we're going to do is go under each BGP instance and just add a network statement for that particular network that we want to have advertised. It's really, really straightforward, nothing too crazy. So we're already on router 3. So let's just go, and I think we're already under the BGP router, so super easy. So we're just going to go network 192.168.3.0, 255. Actually, I think it's a mask. Mask 255, 255, 255.0. We'll just make sure that looks right. Yep, it looks perfect to me. All right. So here, network 192.168, 4.0, mask 255, 255, 255.0. And then in router 2, same thing. network 192.168.2.0 mask 255.255.255.0. And lastly, on router 1, network 192.168.1.0 mask 255.255.255.0. Okay, so with that, I should be able to go do show IP BGP. And there we go. And so we get some interesting information from this. Obviously, with the 0.0.0.0 for next hop, that means self, right? Here we see the IP addresses of next hop as according to the router ID for BGP. Local preference is always interesting. This can be set, and the higher the number, the more preferred it is. Wait is, and this is something that can be sent back and forth. Wait is something that's local. Higher the number for wait, the more preferred that is. So talking about if you had two routes of the same thing, if it had a higher local preference, then that would be taken. If it had a higher wait, that would be taken. And then again, that gets into something that we talked about before. There's actually a whole list of different types of attributes, and they go in priority order. So even though a local preference might be higher than something else, but if it has a weight that's higher on that, then that might be, what it takes. It just really depends. You kind of have to look through all the different things that are being provided there. I think we went over this in the last video, so I'm not really going to hit this up too much, but I did put a link for this in the video description if you want to get into that. Other things interesting here, so path, internal with the I, and this is where you actually can see the AS path information. So you see that this one is coming from 65.502. You see that the 3 network actually started at 65.503 and then went to 65.502 to get to being here in this router. So this is interesting, the way that the path, AS path length kind of works. A shorter path is preferred over a longer path. So in this case, if we had 2 advertisements for this, but it had a shorter path, only one number versus the other, then it would be preferred. And if you didn't like that and you want to do something to alleviate that, then you'd have to mess around with some of the different path metrics that go with that, which actually is something that we're going to do, I believe, in the next task here. But before we wrap this one up, we see that it's being advertised. We do want to make sure that we can ping everything. So let's just 192.168, 4.1 source. Let's do ping 192.168, 4.1 source 192.168, 1.1. So perfect. Perfect. And we could move through all these different devices. To do that, we don't necessarily need to, but I will hop down on router 3 here and just do a similar test back and forth. Ping 192.168, 1.1, source 192.168, 3.1. And this is just these .1s that I'm pinging is just the IP address on the interface VLAN for those subnets. Oh, helps when I don't mess up my source. Let's see. Okay. So we do that. Do 2, 1, 2, and then we'll do 4. Perfect. Okay. Now, that takes care of task 4, task 5. So we're talking about we want to plan a future link between router 1 and router 3. However, we want to make sure that router 1 and router 3 should prefer going through 65.502. So this actually gets back to what I just was talking about, where the path actually would be shorter here, right? It just would be, if you looked at the routing table on this for this subnet and there was a connection here, it would have one route coming from here all the way through and one route coming from here. And this one would be a shorter path because it would just be 65.503 versus the one coming through here would be 65.502 space 65.503. So if we want to make sure that we don't do the short path as the primary, and we want to keep it coming through 6502, both for traffic coming from LAN 1 going to LAN 3 and for traffic from LAN 3 going to LAN 1, then we're going to have to do something about that. We want to make sure that we don't affect any other subnets. So we don't want to affect this guy going around this way or coming around that way. We're just focused on communication between these two subnets. And what makes this interesting and forces us to have to use regex is that we can't use IP ACLs or prefix lists. So what we're going to have to do with this is use regex, and we're going to need to look at modifying either the weight or the local preference attributes. And we kind of talked about those a little bit. I mentioned those here. The weight, it's going to prefer the highest weight. And this value is local to the router, and it's Cisco proprietary. So you won't see this on Juniper or some other type of device like that. The default value is 0 for all routes that are not originated on the router. So that's one way to do it. The other way to do it with local pref is used within the AS. So remember, it's exchanged between iBGP routers, and we prefer the path with the highest local preference. The default value is 100. So if you remember going back and looking at this, do show PBGP. We saw that the weight for 192.168.3.0 is 30,768. This is the default that you get for weight for a route that is locally sourced. Everything else is 0. So in looking at our options, we can use something called AS Path Filters, which are used to perform BGP filtering policy control based on the AS Path attribute. So we can, in essence, look at the traffic coming through, in this case, and we see something coming from 6501 going through 6502. We can set up a filter that matches anything doing this, and then based off of matching that filter, we can modify those different types of attributes. So it's going to use the IP AS Path access list, and then it's going to use a regex expression to match on what we need to match on. Now, I'm going to tell you, the regex stuff can get pretty confusing, especially if you don't use it all the time. So I kind of found this here that might be kind of helpful. Again, put this in the video description. But this kind of gives you a little bit of an idea of different regex expressions you can use to match on different stuff. So this here pretty much will match only prefixes local to the AS. Okay, so it's a subnet that's local to the AS. If this was a star, or if it was a period star, then that's going to use to match all prefixes. You can kind of go down and see matches prefixes from AS51 that's directly connected to our AS, matches prefixes that originated in AS51. The $ at the end ensures that it's the beginning of the AS path. There's a whole bunch of different stuff that you can do, and then also different stuff coming into play with the parentheses dealing with a confederation peer. I would say definitely go poke around, Google BGP regex, and you're going to find a whole bunch of different documents that will help you identify different ways that you can identify and match on traffic. Now, the cool thing is, or the thing that will help us out with this is before we actually identify what we need in the IP AS Path access list, we actually can do show commands with what we think the right regex syntax is. And so if we know what the routes are that we have in mind, we can verify that this particular regex syntax is actually identifying the correct routes that we're looking for. So what we're going to do here is we're going to do show IP BGP. Well, let me actually get out of config mode. Show IP BGP regex P, and then we're on router 3, so we want to look for routes that are coming from 65.501, right? That's going to be what's on router 1 up here, because we're talking about routes advertised through here that go through 65.502. And so what this specific command would look like to get this, it's going to be like this. And again, we're using the parentheses, I think, because of the confederation aspect of this. So 65.502 is what that's going to be going through, and starting from 65.501. And it's a backslash like that, the parentheses, and then the $sign to close that out. So that would be, I think, ensures that it's the beginning of the AS path, right? So that $sign here is ensuring that this is the beginning of the AS path. So if we do this, that does end up showing us the particular route that we're looking for, right? And it's because it matches this path. So we can do the same thing on router 1, doing that in reverse. Let's see, right in here. So in this case, show IP BGP regexp underscore backslash parentheses. And again, remember that it's going through 65.502 and starting from 65.503. And we need to backslash that and the $sign. And it shows us that. Now remember, if we had that direct connect between those, we still would have another route coming for this network, but it wouldn't match the way that this particular path is, right? So we're actually identifying the route that's matching this path because we want to ensure that we actually use this path. So once we match this, then we're able to modify attributes to ensure that this one is ranked higher than the one that's kind of a direct connect. So what we're going to do with this here is now the IP AS Path access list. So what this looks like is IP, let's go config, IP AS Path access list 1 permit, and we pretty much can just copy and paste this. Okay. And then, so based off of having an access list that matches that, we are then going to create a route map. And we were going to modify the weight, not the local preference. So we can go route map. We're going to name it weight. Permit 10. We go match AS path. This is AS path access list 1, so we go AS path 1. And we're going to set the weight to something high within the bounds of what we're allowed to do. So we're going to go 50,000. And you go 40,000, you can go whatever you want to do. Go higher than the default. But remember, anything that's not sourced locally is going to be a 0. So go that. And then we're going to go a second statement here. We'll go 20. And that will just let everything else come in, right? So this route map 1 is going to match on AS path 1, which is this, which is going to look for this AS path. If it matches this, it's going to set the weight to 50. Then the next statement down, anything else is just going to hit that and be permitted. And then we're able to take this and attach it to our neighbor command for routes coming from 65.502, specifically router 2, since that's the direct connection we have between router 1 and that AS. So we're going to go BGP 65501. Oh, router BGP 601. And then we're going to go neighbor 2.2.2.2, route map, weight, and we're going to be applying these to routes that are coming in from this neighbor. Okay. Now, we're going to go do the same thing on router 3. That's going to be a little bit in reverse. And we can get in here. Okay. And since we kind of already walked through the specifics of that, I'm just going to pull these configs over here just so we can copy and paste them. And I'll show you what we're doing here. So in this case, we're matching coming from 65.502 and 65.501. So again, this is going to be the AS path access list. And then we're going to create the route map. And again, this is going to match on the AS path, and it's going to set the weight to 50,000. Then it's going to have a second statement that's going to allow everything else. Okay. Then we're going to go under BGP and do that statement for the neighbor. So this is going back to router 4. Again, we're applying it in an indirection because this is dealing with routes that are coming from that neighbor. Oh, let me get my right router BGP 65503. Let's try that. There we go. Okay. Now we should be able to verify that this change actually did modify, and what we're expecting to see is the weight actually change for that route. So if we do a do show IP BGP, let's see if I'm missing something here. Weight in AS path. This looks good here. 65.502. Right, that looks good. Weight. Route map there looks good. Let's see if there's something else I'm missing someplace else. It might be might have had to exit out of that. Let's see. Show IP BGP. There we go. Yep. So now we're seeing that. We saw that before. We saw that route from for the .1 network that's going over this path, right? Going through 65.502 had a weight of 0. Now it has a weight of 50,000. If we go and do the same up on this, show IP BGP, then we end up seeing the same thing. The 192.168.3 network now has a weight of 50,000. So if we were at some point to go ahead and create a link between here and here, because of the fact that the weight value is that high, and the weight value is one of the first ones that's has the higher precedence, then instead of the traffic initially going from 1 down to 3 like this, it actually would continue to go through here, and vice versa. This traffic would go up through here. So yeah, that pretty much covers everything that we were going to do today. So just quick recap of everything that we hit. We ended up having the lab. We ended up setting up loopback addresses on all the different devices, and then set up OSPF as a IGP between everything, not actually routing the LAN subnets, but everything else. Then after that, we did a little bit of a dive into BGP confederations and why we need to use those in certain instances, especially when we have just a very large iBGP single AS environment. We talked about the differences between that and using route reflectors. When it comes to using a confederation, the benefit there is that you actually can use different types of IGPs within each of the different sub-ASs. So kind of interesting. And then talked about a little bit of the traffic differences as far as how communication between sub-ASs is still treated as iBGP, specifically if it's using the same type of interior gateway protocol, IGP, between all of those internal peers. So kind of cool. Then we went and we set up the BGP confederations. We used loopbacks as the peering points for those, and then made sure that the BGP configuration that we used for the confederation identifier was AS254. So any type of external BGP that would be connecting to any of these particular sub-ASs would actually see it coming from AS254. So we did all that. Once we made sure that that was good to go, then we advertised the different LAN subnets via BGP. And then lastly, we looked at ways that we could modify traffic based off of AS path. Specifically, we couldn't use IP access lists or prefix lists, which meant that we were going to have to use Regex. And we looked at different ways that we could do that, and then modified the weight on the two different devices that we wanted to ensure that traffic that matched that AS path access list was preferred in the way that we wanted. So I think that about covers everything. Does anybody have any questions? This is a pretty good lab, took about an hour. Have a few other BGP labs that I want to do, and then I think I want to do some multi-protocol labs. But I find this stuff to be pretty good. If you like this, this lab was based off of the 101 CCNP lab book. So I kind of use that as a baseline and then modify things a little bit to add some different stuff, and then obviously walk through the background information behind these different things. All right, well, if nobody has anything else, I appreciate everybody dropping in. Leave some comments, share the video with your friends. Make sure you do subscribe to the channel, hit the like button, hit the notification button, all that other good stuff. So, all right, everybody have a good week, and we'll chat soon. Bye.